Hey everyone, welcome to CS 109, the discussion section for the winter quarter of 2021. My name is Tim Janitsos, and I'm the head TA for this discussion section and for the course more generally. The way I conduct my sections is we start off with icebreakers, we go into breakout rooms to work, and then the last part is we all reconvene here, and then I start the recording. So that's the section of the section that we're in right now. So what I'm going to do now is start going over these problems. Everyone feel free to jump in if you'd like. And let me share my screen real quick. So we have Can everyone see my screen? Thumbs up.
Yep.
Awesome. So we have this first question about the inclusion-exclusion principle. So we actually saw this in class the other day when we were talking about just two sets. And what we had said was the inclusion-exclusion principle when applied to two sets means that A union B, and then take the size of that set. So the size of A union B equals the size of A plus the size of B minus the intersection of A and B. And we made sense of that in terms of a diagram, or we can make sense of that in terms of a diagram because you're just taking both circles and then cutting out the middle part. So what this question was trying to get you to think about was how can you reason about the same kind of problem, but not constrained to only two sets? So does anyone have any comments or general lines of approach to justify why the inclusion-exclusion principle when applied to three sets looks like it does here? What do we think?
Sounds to me that if we look at the Venn diagram, we can see that we have the A, B, and C separately. We have to account for the overlapping pairs that are being formed, namely E, D, and F. But by removing all of the pairs, we're also over accounting for G, which would be the intersection of A, B, and C. So we want to add that back in.
Thank you so much. Exactly right. So what he noted was we got A, which is this whole circle, B, which is this whole circle, and then C, which is this whole circle. And if I add them all together naively, I just get overcounting. So double of D, E, and F, but triple of G. So I subtract out these to account for the D, E, and F, but then I take too much out for G, and then I'm left with a G that's at 0 again. So that's why I add the intersection of all of them to get back that middle piece. The same kind of reasoning you can apply to larger numbers of sets, but we're not going to hold you accountable to much more than this in class. The next question was about choosing a set of fish from a fish tank. So suppose there are 7 blue fish, 4 red fish, and 8 green fish in the large fishing tank. You drop a net into it and end up with 6 fish. What is the probability you get 2 of each color? What did we think about this one? So one thing to note here is that this problem said the word probability. It asked, what is the probability that you get a certain outcome, right? And whenever we see that, that tells us that we need to be reasoning about the set of things we're trying to count divided by the set of all ways we could have possibly counted. With that in mind, does anybody have an approach for this problem?
Our group did, on the top, we had the distinctions, and we made the event in which all of the colors you're going to choose 2. So we did 7 choose 2, multiplied by 4 choose 2, multiplied by 8 choose 2, all over the total number of fish of 19, where we choose 6.
Excellent. Perfect. Did everyone hear that? So basically, the numerator was just the things we were accounting for. The denominator was all the ways we could have chosen it, which was 19 choose 6. And then the numerator was just taking into account the two that we chose of each color and multiplying them together. Okay, awesome. So straightforward problem there. This next one is interesting. So we got some true false. And one thing I wanted to note, which I'm not sure if I mentioned on the outset, and apologies if I did. We have some of these true false statements in our discussion sections often. And whenever I write these, I'm using certain logical operators. And so this operator means implies. So we're saying like, does this thing on the left imply the thing on the right, basically? And you can consider it taking the lowest precedence. So evaluate whatever's on the left, evaluate whatever's on the right, and then ask the question: does the thing on the left imply the thing on the right? And then we also have this other operator that looks like a caret kind of thing, a pointy thing, and that is logical and. So the question I'm asking here is the probability of A equaling 0.4 and the probability of B equaling 0.6 imply that they're complements? That's basically how you would read that in English. So what do we think about this question? Well, let's start. Now that I got that logical notation out of the way, let's just start with the first one. Probability of A plus probability of A complement equaling 1. What do we think about that? True
You
or
said
false?
that's true. True.
True. Yep. Exactly. Sort of definition of complements. What about this next one? Probability of A intersection B plus probability of A intersection B complement equaling 1. What do we think? A little bit less confident, but looks like no. Yeah, exactly. And actually, let me see if I can share my screen real quick. So whenever we reason about these kind of true false statements, it's always helpful to draw out a diagram. So can everyone see my screen, by the way?
Yep.
Yes.
Okay, you can see my whiteboard, great. So this this problem basically we have two events. We have A and we have B. And it says probability of A intersection B, which is going to be this part, plus probability of A intersection B complement. Well, that's just going to be what? Can anyone tell me? What is A intersection B complement? What part should I be shading in?
Like just A.
The part of A that's not in B. Yep. Yep, right here. So does that equal 1? No, it doesn't. But interestingly, it does equal A, doesn't it? And so this is a sort of useful identity that is going to be kind of recurring in class. Whenever you want to figure out the probability of an event A, but you don't have that event, you only have it in terms of its intersection with other events, you can actually break it up like this. You can figure out what A is by piecing together the shards of it. All right. So that's for A. And then, and that's for this second question. And then for this third one, that's the one that I had was referencing earlier with the logical notations there. So we have probability of A equaling 0.4 and probability of B equaling 0.6 implies that A and B are complements. Is that true?
No.
Nope.
Because A and B aren't necessarily mutually exclusive.
Exactly. So as you just mentioned, we don't have to assume that they're going to be mutually exclusive. So, even though that they add up to 1, they could overlap in some way. Okay, great. Got just a little bit of time for this birthday problem. Did anyone have an approach for this birthday problem? So what is the probability that n people in the class, that of n people in the class, at least 2 share a birthday? How do we approach this? Actually, since we only have a little bit of time remaining, I will just sort of work through it, and anyone can kind of flag me or interrupt me as need be. So one of the ways we could start is it's asking about the probability that at least 2 people, right? How do we count something like that? Do you know how to count something like that? Because I don't. It sounds like really hard. At least 2 people, like as like one sort of thing. So when we have something like this that it's kind of hard to reason about, let's try to see if we can break it up into pieces and maybe we can count those, right? So one way to do this is we could break it up into counting all the ways that 2 people could share a birthday, right? and then counting all the ways that 3 people could share a birthday, and then counting all the ways that 4, all the way up to n, right? That's a first pass approach, but it's not ideal. We're going to have a lot of terms if we try to reason about it that way. So what's a better way? The approach that I just said, there's nothing wrong with it in terms of correctness. In terms of expediency, how could we improve on it? Anyone have any ideas?
We could do 1 minus the probability that no 2 people share the same birthday.
Yes, exactly, exactly. Thanks a lot. So that's exactly how we're going to approach this, where instead of trying to say 2 or more, right, we're going to say, what's the probability that no 2 people share a birthday? So everybody's got their own sort of birthday, all right? And this problem, since it's asking about a probability, what does that imply? Do we remember what we had mentioned moments ago about when we see the keyword probability, what that entails for our answer here?
You have to divide the event space over the sample space.
Exactly. You have to divide the event space over the sample space. So what we're going to have is something of the form 1 minus, event space over sample space kind of thing, right? Now, how do we think about the sample space? Well, what are all the ways that people can be assigned birthdays? Well, everyone is distinct, right? And there are 365 days, and there are, what is it, n? I think we just said n people, right? So that's just going to be 365 to the n. Okay. What about this event space? This is a little bit trickier, and then we'll end with this. I don't want to keep you guys too much over time. Anybody? So the way we're going to do this is that you could think about it as like 365 choose n. That might be a good way to approach it, right? Like if I had 365 days and, I was putting people, on these days, well, then that seems somewhat reasonable. And then that would be my numerator and I'd be good. The problem with that is that this does not properly account for the fact that the assignment of people on birthdays is different. Even I want to count different situations, even when people have swapped birthdays, right? So it's not just a matter of assigning January 13th and January 15th and January 27th as my 3 people, right? I'm counting that as a permutation, but I also want to count, well, what if Bill and Janet switch, right? I want to count that as something different. And so for that reason, this 365 choose n is not going to work. This would turn into 365 factorial minus, or divided by, what is it, 365 minus n factorial times n factorial, right? What I'm arguing is that this is not quite right. The correct answer turns out to be almost this exactly, but without this term. Whoops. My Wacom tablet's glitchy. This term gone, right? And the reason is because when I'm assigning the birthdays to people, I'm going to have 365 for the first one, and then 364 for the second, right? So 365 times 364 times 363, right? All the way down until I get to the 365 minus n. And then I run out of people to assign birthdays to. But the fact that I had assigned them to specific birthdays mattered. And I could have, again, if I moved different people to have different birthdays, but with the same assignment of birthdays to all people, I would want to count that as something different. Okay, I'm not going to keep you much longer. Let me stop the recording here. And thank you very much for your attendance and participation. Thanks a lot, guys.
Thank you.